Overfitting is when we construct a model that too closely follows the noise or variability in our data and doesn't generalize to new data sets. Fundamentally, our goal in constructing a model is to be able to make predictions about new data. However, when training a model, we typically do not have access to the data on which we will be testing, and so we are forced to instead try to optimize or fit the model to the data we have. So in this part of the notebook, I want to walk through what happens when we overfit. Now, we actually already saw a little bit of an example of overfitting earlier when we went to too many features. This is actually a common way to overfit. Here I want to examine a model which uses fewer features, and so we don't have this underdetermined system, so the number of features will be less than the number of examples. And I still want to show how this can overfit and some of the implications of that. So as before, I'm going to use these radial basis functions, but instead of using 20 different locations or 4 locations, I'm going to use 7 different RBF locations. So these are my bump locations here. And now I'm going to, just as before, I'm going to construct a phi. So this is my phi matrix, to give an idea. So this is using the phi line RBF with these 7 locations. And there are 7 locations here, but the line part of this feature function will add an additional slope and intercept. And so we'll get 9 features. So we have a 9 by 9 matrix. So we have a 9 by 9 matrix. So hopefully this will be full rank. And now when we go to construct a linear model, which we'll do here, we've constructed a linear model with our 7 bump locations or 7 RBF locations. And we can fit this model to our data. And these are the resulting learned theta hat parameters. So now we can compute the loss for this new model on our data set. And we see we get a loss that's very close to 0. So the data is now well fit by this model. And just to visualize the model we just constructed, we'll go ahead and include the new model as well as some of our earlier models. And so here's the orange line for the latest model. Just as before, when we went to 20 RBF features, we have a line that does seem to go off to extreme points on our plot. This line looks similar to what we saw when we used 20 RBF features. But here we're using something where there are 7 RBF features where we can actually solve the system of linear equations. And just as before, it goes through all the data points. So it's not surprising that we have a loss of 0. But what is a little bit concerning is that while it goes through all the data points, it also seems to behave erratically between these data points. In fact, we zoom out a little bit. We see it goes off to kind of extremes, and it's got these kind of weird bumps in here. So this is our model, and it seems to perform well, at least on our training data. We can compare the loss of this model with some of the other models we've trained earlier. And so I'll go ahead and construct the list of models we have so far. And these are each of the model objects. Their corresponding names here. And then I can compute the loss for each of these. I'll do that once more for each of the models in this little list comprehension. And so then we can plot the model, its name, and its corresponding loss. And so here's our line model, our 4 RBF, our line plus 4 radial basis functions, and then a line plus 7 radial basis functions. And we see that the loss goes to essentially 0. So we did minimize the training loss. And so in some metric, we might imagine this is the best model. But again, as you look here, this model doesn't, while it does fit all the data, it doesn't really seem to follow any coherent trend. So because our ultimate goal isn't really to make predictions about the training data, instead to be able to make predictions about future test data points, what we might want to do is look at some data that we didn't use during training. So this is typically called a test data set. And so we can obtain, in fact, I created an additional collection of test data points. I believe there are about 100 test data points. Yeah, so there are 100 test data points here. And I can plot these 100 test data points drawn from the same process. And this is what the 100 test data points look like. So each of these red crosses is one of our test data points. And now we can look at how the new models compare on this test data. So here I'm going to extract the X and Y matrices from this test data. I'll loop over my models evaluating the test on each of these points. Okay, so this is the test loss the loss of each of the models on the test data set. And so we can see that the losses actually they get pretty large for some of our models. We can now plot these, the training loss and test loss side by side, and this is what we get. And so the training loss is consistently lower than the test loss. And this is something we'd expect because we are trying to optimize for the training loss, not the test loss. And then what's maybe more interesting is that while the training loss goes up and then seems to go down as we go to this line plus 4 RBF, the test loss seems to consistently go up. So as in this direction, we're improving our training loss, we're actually making the test loss much worse. And in fact, here I had to truncate the plot. The test loss goes out quite a bit. So if we zoom out a bit and just keep zooming out, we can't really get to the top of this test loss here. So this bar is pretty tall, right? So yeah, so this model doesn't, this line plus 7 RBF features actually performs really poorly on our test data set. So this is an example of overfitting where we've really improved the accuracy or the quality of our model on our training data set, but produced a model which is much worse. So more generally, there's this idea of our ability to generalize to new data. And maybe the best way to think about this is through the following plot. And in some sense, this is a plot that you want to be able to remember. So if we think about our error in the model, which could also be thought of as the loss. So this is our loss on the y-axis. And on the x-axis here, we have the complexity. So for this example, more features is greater complexity. So this could be a number of features. We'll actually see in other cases where there are other metrics that we might use to describe the complexity of our model. Then the goal in modeling is to try to find this sweet spot of best fit. If we choose a model which doesn't have enough features, then in some sense what's going to happen is we're going to get a training error that's going to be really high and a test error on new data that'll also be very high. Then as we add more features or increase our model complexity, we're going to bring that test error and training error down. And then at some point, as we add too many features, we start to overfit, or as we increase our model complexity, we start to overfit. Our test error will actually start to go up, but our training error will continue to go down. Right? So we have to try to find the sweet spot. And doing that actually requires an algorithm, which we'll present in the next lecture, called cross-validation, which will allow us to essentially keep a training set where we're going to continue to train, but then split off a little bit of that training data to use as a test data set to actually construct this orange curve here and get an idea of what our true test error would be. Now, unfortunately, we don't ever have access to our true test error because we don't know what the future holds. And so we'd really like this test error to reflect the future that will be tested on. But again, we don't know that. So what we'll often do is take our training data and split off a little bit and call that our test data set. And again, the point is we won't actually use that split off test data set during training. All right, so that concludes the notebook on some of the pitfalls in feature engineering. The next notebook will talk a bit more about the train test split and then the process of cross-validation.